Category O, Lecture 22, Twisted or Shuffled Verma modules. Let us start with the setup. Let G be a semi-simple finite-dimensional complex Lie algebra with a fixed triangular decomposition into the negative part and minus, the Cartan subalgebra H, and the positive part and plus. Consider the BGG category O associated to this triangular decomposition, and let O0 be the principal block of O. This principal block has a graded lift, which we denote by O0 upper Z. And also we denote by W the Wild group of G. We have the following structural modules in the principal block O0. LW denote the simple highest weight module with highest weight W.0. PW is the indecomposable projective cover of LW. IW is the indecomposable injective envelope of LW. Delta W is the Verma module with highest weight W.0. And nabla W is a dual Verma module with highest weight W.0. And finally TW is a tilting module with highest weight W.0. There are many functors which act on the principal block O0. The first one is the simple preserving duality denoted by star. Then we have projective functors. Indecomposable projective functors are indexed by elements in W, and the functor theta W denotes the unique indecomposable projective functor, which sends PE to PW. Further, we have defined shuffling functors CS for each simple reflection S as the cokernel of the adjunction morphism from the identity functor theta E to the translation theta S through the S wall. Further, for a reduced expression W is equal to S1, S2, and so on Sk of an element W in W, we denote by CW the composition CS1 followed by CS2 and so on followed by CSK. Please note that the composition is in the reversed order compared to the original reduced expression. And we know that up to isomorphism, the functor CW does not depend on the choice of a reduced expression. Similarly, we have co-shuffling functors Ks defined as kernels of the adjunction morphisms from the translation theta S through the S wall to the identity, and this functor is defined for each S in S. And similarly to shuffling, if W is an element in W, we choose a reduced expression and define the corresponding co-shuffling KW as a composition of co-shufflings for simple elements in this reduced expression, reversing the order of the reduced expression. Then we have Joseph's completion functors JW, which are defined for an element W in W using Bernstein-Gelfand equivalence. So JW is a composition of the functor of taking locally at finite homomorphism from delta W to blank, followed by tensoring over U of G with the dominant Verma module. Finally, we have defined twisting functor TS for each S in S. So the definition uses localization of the universal enveloping algebra and then twisting by certain automorphisms. And for each reduced expression of W, we define the corresponding twisting functor TW as the composition of the elementary twisting functors in the same order as the reduced expression. In other words, this tells us that twisting act on the left on our category, while shuffling and co-shuffling, they act on the right. We know that shuffling is left adjoint to co-shuffling and that twisting is left adjoint to Joseph's completion. We also know that shuffling is the conjugation of the co-shuffling by duality, and similarly twisting is the conjugation of Joseph's completion by duality. We also have graded normalizations of the shuffling and the twisting functors using the property that Cs of delta E is equal to delta S, and similarly Ts of delta E is equal to delta S as graded modules. This defines the gradients on all CW, KW, TS, and JS uniquely using the definitions and adjunctions. Now we are ready to define the main protagonists of this lecture, shuffled or twisted Verma modules. For two elements x and y in W, we define the module delta x, y as the y shuffling of the x twisting of the dominant Verma module delta E. Please recall that we know that twisting and shuffling functors commute. Therefore, delta xy is actually the x twisting of the y shuffling of delta E. Now, these modules are called shuffled or twisted Verma modules for the following reasons. We know that when we shuffle by y the dominant Verma module delta E, we get the Verma module delta y. Therefore, delta xy is the x twisting of delta y. So it's a twisted Verma module. But similarly, we know that delta x is the x twisting of delta E. Therefore, delta xy is the y shuffling of delta x, and so it's a shuffled Verma module. So as shuffled Verma modules, these were studied by Ronald Irving in his paper on shuffled Verma modules in 1993. And as twisted Verma modules, they were studied by Anderson and Lauritsen in their paper Twisted Verma modules in 2000. So we start by describing the connection between twisted Verma modules and the principal series Harish-Chandra bimodules. Recall that we have the category H of Harish-Chandra bimodules. So these are finitely generated bimodules on which the adjoint action is locally finite and has finite multiplicities. And we also have the Bernstein-Gelfand equivalence between the principal block O0 and the category H001 infinity. This is a certain subcategory of Harish-Chandra bimodules. And this equivalence is given by taking the at-finite homomorphisms from delta E to blanks. This goes from O0 to Harish-Chandra bimodules. And the functor back is just tensoring over UG with the dominant Verma module delta E. Also recall that we know that for any pair of modules M and N in O, the bimodule LMN is a Harish-Chandra bimodule. So the principal series Harish-Chandra bimodules are defined as L from delta x to nabla y for all x, y in W. And the origin of this is in the representation theory of real semisimple linear Lie groups. Our main observation about the connection of twisted Verma modules and principal series Harish-Chandra bimodules is the following statement by Irving, that the Bernstein-Gelfand equivalence maps the module delta xy to the bimodule L delta xw0, nabla w0y. So let us prove it. To start with, let us recall that the antidominant Verma is self-dual, so it coincides with the antidominant dual Verma module, and it's simple, of course. Next, recall that L delta W nabla W, which is the same as L delta W delta W, is equal to L delta E by Costant's problem for Verma modules. This means that Bernstein-Gelfand equivalence maps the dominant Verma module to the bimodule L delta W0 nabla W0. We also know that the BG equivalence intertwines the shuffling functor Cy on the principal block O0 with the shuffling of the second component of the bimodule. And we know that Cy of nabla W0 is equal to nabla W0y. So the first component of L is contravariant because it's a Hom functor. And the Bernstein-Gelfand equivalence therefore intertwines twisting Tx with the co-shuffling of the first component of the ad-finite Hom. And we know that the co-shuffling Kx of delta W0 is equal to delta x W0. So putting all these things together, we exactly get Irving's claim that delta xy is mapped to L, delta x w0, nabla w0, y. Before we proceed, we would need the following lemma. For any element w in W, the evaluation of the adjunction morphism from JW inverse to the identity at TWW0. So when we evaluate, this becomes a natural transformation from JW to TWW0. So the claim is that this natural transformation is an isomorphism on the category of modules which have Verma flag. First of all, we know that if we evaluate this natural transformation at the antidominant Verma module delta W0, this evaluation is clearly non-zero because delta W0 is not killed by JW and by TW inverse. So this evaluation is non-zero, and hence it's an isomorphism because both sides of the evaluation are isomorphic to nabla W, and this module has trivial endomorphism ring. Next, since all functors involved in the evaluation commute with projective functors, it follows that eta t is an isomorphism when restricted for any tilting module T, because all indecomposable tiltings can be obtained from delta W0 by using projective functors, and all morphisms between tilting modules are evaluations of natural transformations between projective functors at delta W0. So now we can take a module M in F delta and consider its two-step tilting presentation. Since twisting functors are exact on F delta, the functor JW-TW0 is left exact on F delta, and therefore the claim of the lemma follows from the 5 lemma. We get a commutative diagram with exact rows where the evaluation at T1 and T2 are isomorphisms, therefore the evaluation at M will also be an isomorphism. So now, using this lemma, we can describe the interaction of twisted or shuffled Verma modules with the duality. The claim is that the dual of delta xy is delta xw0, w0, y for all x and y in W. Proof. Let's compute the dual of delta xy. So this is equal to, so the definition of delta xy, it's delta e, y shuffled and then x twisted, and then we have the duality. So we insert the square of the duality between the twisting and shuffling and between the shuffling and the module. So we get duality tx duality, duality cy duality, and then the dual of delta e. So we know that duality tx duality is jx, and duality cy duality is ky, and the dual of delta e is nabla e. We know that ky of nabla e is nabla y. We know that nabla y is isomorphic to TW0 of delta W0y. And using the previous lemma, since delta W0y has a Verma flag, we can write Jx TW0 delta W0y as T xw0 delta W0y. Finally, we know that delta W0y is CW0y applied to delta E, and now we have the definition of delta xw0, comma W0y. And here, in the crucial place, here in the middle, we used the previous lemma. So let us look at the SL3 example. In the case of SL3, the while group W consists of E, S, T, ST, TS, and W0. And here is a table of all shuffled and twisted Verma modules given in the graded picture. Here is the full table, and we have seen a version of this table once before. And in this table, we see that in the first row we have Verma modules, in the first column we have Verma modules, in the last row we have dual Verma modules, in the last column we have dual Verma modules, and two pairs of dual modules are given in color. So here is a module delta SS, and here is a module delta TSST, so they are dual to each other. as you can see from the picture. And similarly, here we have the module delta STT and the module delta T TS. They're also dual to each other, as you can see from the picture. So our next property for shuffled Verma modules is the following proposition. For any xy in W, the endomorphism algebra of delta xy is trivial, so it coincides with the base field. In particular, the module delta xy is indecomposable. To prove this, let us recall that delta xy is Tx of delta y. We know that the endomorphism algebra of any Verma module is trivial, and we also know that twisting functors are acyclic on Verma modules, so there are no homology when you apply twisting to a Verma module. So therefore, twisting delta y is the same thing as derived twisting delta y. But the derived functor is a self-equivalence of the bounded derived category, which implies that the endomorphism algebra of delta xy is the same as the endomorphism algebra of delta y, which is the complex numbers. And the only idempotencies in C are 0 and 1, which implies that delta xy is indecomposable. The next interesting property of twisted Verma modules is associativity. Assume that x and y are two elements in W, and S is a simple reflection such that xs is greater than x, and sy is greater than y. Then the module delta xs, y is isomorphic to the module delta x, sy. For the proof, we again compute. So delta xs, y is txs times cy of delta E. We can write txs as tx ts, and ts of course commutes with cy. So now when we apply ts to delta E, we get delta s, but now we can rewrite delta s as cs applied to delta E. And then the composition of cy and cs gives us csy, and now we readily see the definition of delta x, sy. The next property of shuffled Verma modules is given in the following proposition. Assume that x and y are elements in W, and s is in S such that ys is greater than y. Then there is a short exact sequence, so delta xy is a submodule of theta s delta xy, and the cokernel is delta x, ys, and the first inclusion is given by the adjunction morphism for S evaluated at delta x, y. Proof. We already know that such a sequence exists if x is E, that is for usual Verma modules. And this sequence is of course a sequence of modules with Verma flag, and since twisting functors are exact on modules with Verma flag, we can apply Tx to the sequence and get exactly the sequence from the formulation. So one only has to note that since twisting functors commute with projective functors, applying Ts to the adjunction morphism Hs evaluated at delta y, we will get exactly the adjunction morphism in the formulation of the proposition. Now we can discuss the character of twisted or shuffled Verma modules. So the claim is that for any xy in W, the image of delta xy in the Grothendieck group of O0 is equal to the image of delta xy. So the character of delta x, y coincides with the character of the Verma module delta x, y. Please note that this is an ungraded statement. It's important that here we speak about the Grothendieck group of O0. An analog of this statement in O0z is not true. To prove the statement, we proceed by induction on L of y. The basis of the induction is the observation that delta x, e is Tx delta E, which is equal to delta x, and so the claim is obvious in the case y is equal to the identity. For the induction step, let us take y in W and a simple reflection S such that ys is greater than W. Now let us look at this short exact sequence in the proposition. So looking at that short exact sequence, from that sequence we get that the image in the Grothendieck group of the right term delta x comma ys is equal to the difference between the image of theta s delta xy and the image of delta xy. So by induction, we know that the image of delta x comma y is equal to the class of delta xy. And we also know that the linear transformation of the Grothendieck group given by theta s coincides with the right multiplication by the element e plus s. And so the class in the Grothendieck group of theta s delta xy is equal to the class of delta xy times e plus s. So now when we subtract once the class of delta xy, what remains is the class of delta xy times s, and this is equal to the class of delta xys, which completes the proof of this proposition. So now we can formulate the uniqueness statement about twisted Verma modules. Theorem due to Anderson and Lauritsen. It says that the properties that delta EE is equal to delta E, the original normalization. Then the associativity properties that delta xs comma y is equal to delta x comma sy when xs is greater than x and sy is greater than y. And finally, the property that there is a short exact sequence, as in the proposition before. So these three properties define the family delta xy, where x and y are elements in W uniquely up to isomorphism. Let us now prove this statement. The first step of the proof is that starting from the property A, so that delta EE is equal to delta E, and using the short exact sequence in the property C, by induction on the lengths of y, we get that delta E comma y is equal to delta y for all y in W. Now using property B, we obtain that delta x comma e is equal to delta e comma x, which is equal to delta x for all x in W. And finally, starting from delta x comma e is equal to delta x, we again can use property C inductively with respect to the lengths of y to define delta x comma y uniquely up to isomorphism for all x and y. Let us note that Anderson and Lauritsen list one additional property in their statement, namely the property that for x, y in W and s in S such that ys is greater than y, the module theta s delta x, y is isomorphic to theta s delta x, ys. But this property follows from property C using the fact that theta s squared is equal to theta s plus theta s. The next important property of twisted Verma modules is the so-called Gelebenko-Duflo-Joseph exact sequence. Theorem: for x, y in W and s in S such that xs is greater than x and sy is greater than y, there is an exact sequence with 4 terms. So 0 goes to delta x comma sy, this goes to delta x comma y, this goes to delta xs comma sy, and this goes to delta xs comma y, and this goes to 0. Note that the extreme terms delta x comma sy and delta xs comma y are isomorphic. So this was one of the properties which we proved before. So for example, if we consider the Lie algebra SL2 and take x and y to be the identity, this exact sequence reduces to delta s is a submodule of delta e, which is mapped to nabla e, and the quotient is nabla s. So this is a 4-term exact sequence. And the reference for this statement is Joseph's paper about Enright's functor in O and Duflo's paper about representations of semi-simple Lie groups. So let us now discuss how to construct this exact sequence. Using parabolic induction from SL2, so we can take the SL2 example, and this via the parabolic induction, this gives the 4-term exact sequence. Delta e comma s goes to delta ee, goes to delta s comma s, and this goes to delta s comma e to 0. And our claim is that now we can take the sequence and apply Tx Cy, and the outcome will be an exact sequence. And that the modules are exactly as given in the original sequence in the formulation. This follows directly from the definition. So we need to prove that applying to this exact sequence, Tx Cy, we get an exact sequence. So we need to prove exactness. So this is a 4-term sequence. We split it into 2 short exact sequences. The first sequence is that delta S is a submodule of delta E with a quotient delta E over delta S. And the second short exact sequence is that delta S comma S surjects onto delta S, and the kernel is delta E over delta S. So let us first apply shuffling to these sequences. Shuffling is right exact, so we get 2 right exact sequences. So in the first sequence, we have here the map from delta Sy to delta Y, and we know that any non-zero home between Verma modules is injective. So the first sequence is actually short exact. So now let's look at the second sequence. So the second sequence is right exact, and if it's not exact, then the next term should be the homology of the shuffling functor evaluated at the Verma module delta Sy. But we know that shuffling is the other side of twisting, and twisting is acyclic on Verma modules. So the homology of shuffling functors on Verma modules, similarly to the homology of twisting functors on Verma modules, vanish. Therefore, we actually have 2 short exact sequences as indicated here. So now we want to twist these short exact sequences. So for the second sequence, we again twist and is right exact. We get a right exact sequence. And if it's not exact, then the next term should be the homology of twisting at a Verma module. This is 0. So twisting of the second short exact sequence is actually exact. We are left to prove that when we twist the first short exact sequence, we get a left exact sequence, and the next term should be the first homology of Tx evaluated at the module Cy of delta E modulo delta S. So this homology can be computed using the second exact sequence. So from the second exact sequence and the claim that the all homology of twisting vanishes when evaluated at delta Sy, we get that the first homology of Tx evaluated at Cy of delta E modulo delta S is isomorphic to the first homology of Tx evaluated at Cy of delta Ss. So these are the 2 modules, and here the first homologies will be isomorphic because they are surrounded by homologies of T evaluated at delta. Now the module Cy applied to delta Ss is the same thing as Ts applied to Cy delta Es, and this is Ts of the Verma module. And we are in the situation where Xs is greater than X. So we get the first homology, more or less, of twisting functor evaluated at the Verma module. And this clearly vanishes. So this implies that this homology vanishes, so this homology vanishes, so evaluation of twisting at the first short exact sequence is short exact. Next, let us discuss twisted filtrations of tilting modules. The theorem, due to myself from 2003, for each x and w, every tilting module in the principal block O0 has a filtration with subquotients of the form delta xy, where y is an arbitrary element in w. So x is fixed, but y can vary. Proof: denote by w the element x inverse w0. For any element a in w, the module theta a delta w has a Verma flag. This is because delta w is a Verma module and projective functors preserve fw. Applying Tx to this module and noting that Tx is exact on modules with Verma flag, we get a module with an x-twisted Verma flag. And using the twisting commutes with projective functors, we can also compute that Tx applied to theta A delta W is the same as theta A applied to Tx delta W. Because of our choice of W, this is theta A applied to delta W0, which is T W0A. So this means that all indecomposable tilting modules have a filtration with subquotients of the form delta x, y, where y can vary. So the reference for this is the paper Twisted and Shuffled Filtrations on Tilting Modules from 2003. So we have now discussed twisted filtrations. Now we go to shuffled filtrations. The theorem from that paper: for any y and w, every tilting module in O0 has a filtration with subquotients of the form delta x, y, where y can now vary inside w. The proof of this theorem is a little bit more complicated than for twisted filtrations, so let's discuss some notation before we can do the proof. We denote by Fy the full subcategory of O0, which consists of all modules that have a filtration with subquotients of the form delta x, y, where x varies inside the while group. So for example, Fe is just F delta because delta x, e is delta x. So these are the Verma modules. Also, Fw0 is just F nabla because delta x, w0 is a dual Verma module. So as special cases, we have both F delta and F nabla. So this is some kind of generalization of them. And more or less from the definitions, it is easy to see that if S is a simple reflection such that Ys is greater than Y, then we have mutually inverse equivalences of categories. So Fy is equivalent to Fys, where the equivalence is given by applying Cs from Fy to Fys and applying Ks back. Consequence of this, that all categories Fy are additive and idempotent split, since Fe is such a category. So now we are ready to prove the theorem. Denote by A the intersection of all Fy's over all y in W. So from the previous observation, we know that A is additive and idempotent split. Also clearly A is a subcategory of tilting modules because F delta and F nabla are special cases of Fy's. Clearly A contains TW0 because this module is a y shuffled Verma module for any y. And finally, any object in A is clearly self-dual because the duality preserves a class of twisted Verma modules. A small lemma: for any S in S, the translation functor theta S preserves A. So we need to prove that theta SA belongs to this intersection. So if we take y such that Ys is greater than y, then the fact that M is in Fy implies that M is a submodule of theta Sm, and the quotient is by definition Cs of M. So therefore, for such y, M in A implies that theta Sm belongs to Fys. So theta Sm is filtered by all Fys, where y satisfies this condition. But since any module in M is self-dual, we can apply to theta Sm the duality, which gives us the same module, but the index of our Fys, when we apply the duality, needs to be changed to W0Ys. And then this gives us exactly the opposite of this condition. So now, using this lemma, we can prove the theorem about shuffled filtrations of tilting modules. Since any tilting module is a summand of some translation of TW0, and since A contains TW0, the claim of the theorem follows from this lemma. Here is an SL3 example. In the case of SL3, W consists of in, S, T, ST, TS, and W0. So here is a list of ST-twisted Verma modules, delta ST, y. So this is just taken from the previous example where we had all twisted Verma modules. And here is the picture of ST-twisted Verma flex on all tilting modules. So all ST-twisted Verma modules are given by their colors. So here is the picture of ST-twisted Verma flex on indecomposable tilting modules. So the indecomposable tilting module TW0 is delta ST, S. So TST has delta ST, S on top, and then the module delta ST, E in the socle. TS has delta ST, ST on top and delta ST, S in the socle. TS has delta ST, ST on top, and then in the middle delta ST, S and delta ST, T, and then delta ST, E in the socle. So similarly, TT has delta STW0 on top, and then delta STST and delta STS in the middle, and delta STE in the socle. The tilting module TE has delta STW0 on top, delta STTS in the middle, delta STST in the middle, and then underneath them we have delta STS and delta STT, and then in the socle we have delta STE. So let us finish with some questions for PhD students. Question number 1. Prove using twisting functors, but not Coston's problem for Verma modules, that all bimodules L delta X for X and W are isomorphic. Question number 2. Check using the SL2 nature of GS and TS that the junction morphism theta E to the composition of GS-TS is an isomorphism on S-infinite modules, that is on modules which do not have any Lx with Sx greater than x in the socle. Question number 3. Give full details of the proof that all CW where W and W are acyclic on Verma modules. Question number 4. Give full details in the proof that for Y in W and S in S, such that Ys is greater than Y, there are mutually inverse equivalences of categories between Fy and Fys given by the Schafflin CS and the Koshaflin KS. And question number 5. Compute all twisted and shuffled filtrations on all tilting modules for SL3. Thank you very much and see you next time.